But it could be besides just vapor pressure and boiling point, more of those. You just were using those as examples. Okay, perfect. Oh, sorry, go for it.
On periodic trends, were you done? Yeah.
Yeah, I think so.
For periodic trends like ionization energy and like electronegativity, should we use like the general rule that's like as you go right it increases and up it increases, or should we look at like the full and half full subshells and like are those exceptions or are those part of the rule?
Those are exceptions. So when you're looking at periodic trends for any of your trends, you should know the general rule of getting larger as you go across the table. If somebody expected you to answer something about being a half shell or a filled shell, then you would be given a difference in their electronegativity, or you would be told their ionization energy. So based on the fact that nitrogen's ionization energy is lower, explain why that might be the case. And if it goes against the trend, then you need to come up with the reason why, which is then the reason would be half-shelled. The lower energy configuration is one in which you have electrons that are in a half-shell, filled shell or a filled shell. So ionization energy, I think you were asking me, so I'm just gonna go ahead and just make up numbers. Team. Okay, so if I didn't have the smartboard here and I were to continue writing numbers that were like close to this one. So what Amira was asking about a minute ago had to do with the concept of ionization energy and how typically when we talk about ionization energy, we're referring to the first ionization energy, which simply means ionization energy is going to be you removed one electron. From your atom. But you could have a second or a third or a fourth or a fifth or whatever ionization energies. Each additional ionization energy, when you remove the second electron, then that becomes your second ionization energy. And it will always take more energy to remove an electron. Always. It is always going to take more energy. So you'll see that it increases. So third IE, so on and so forth. It will always increase energy. And so if you think about that, what we're talking about is we've got our positive nucleus. Remember, this has my nuclear charge. And the whole reason that our electrons are able to stay where they are able to stay is because of your nucleus and what's happening there. And so as you have these orbitals that are around the outside, which obviously aren't actually orbitals in circles like that, but it's much easier to draw than anything else. So my outer electrons, right? So ionization energy says I've removed one electron. When I removed one electron, I did not change my nucleus in any way. So my nuclear charge stayed the same, but my electrons on the outside were decreased. So I had fewer repulsions between my electrons and allowed those electrons to get a little bit closer, no matter where they came from my atom. And so that means that since they're closer, Coulombic attractions tell us that the closer things are, the greater those attractions are. So because your nuclear charge didn't decrease along with your losing your electrons, that caused your orbital, to come in closer, causing that to have a greater attraction, causing it to always require more energy. So then you can use your ionization energies. These are going to be your successive ionization energies in a row, and for an element in, like, let's say, one of the particular rows on the periodic table. Since I just made this up, I'm just going with it. And so when you're looking at it, this is how much energy it took to remove your first electron, second, third, fourth, fifth, sixth electrons. Okay, and then like I said, I would have kept going, but I ran out of space. So if it took 200 probably joules of energy to remove the first one, 350, you'll notice that it increases. What do you notice happens as it goes? So I removed my first one. Here, now I've removed my second one. Here's my third one. My fourth one. I shouldn't have a fifth one. This would be where my fifth one would be. How do I know that my fifth one was inside here and not outside here? What do you mean by it, Joe?
The ionization energy is a huge difference between the
Yeah, from here to here is a giant difference in ionization energy. So the difference between those two is a sign that these guys are all valence electrons. They're in my outermost, and then I'm moving into my core electrons because they take quite a bit more energy to remove. You'll see like 400 to 700, that was a little bit of a jump, but it wasn't nearly as large as 700 to 1400. So you're going to be looking for where you have the largest gap, the largest change in your energy. And then that's going to be your clue that that was your first valence shell that was lost, and then the rest of them are going to be your core electrons. Mira, does that sound like what you were talking about? Okay. Kind of covers a few different topics in that question. Zane, did you have a question? Okay.
So can you also explain like effective nuclear charge?
Yep, so if we were to go back to this picture right here. So nuclear charge is just going to be how many protons are in our nucleus. When we go to look for effective nuclear charge, we're going to talk about effective nuclear charge and shielding together. So your effective nuclear charge is typically measured in Z, and it's like how well your nucleus is able to attract the outer electrons. So not just what its charge is, but also how it's being balanced. And what you're talking about there is shielding. And shielding is the idea that your core electrons are able to interfere with the attractions for the outermost electrons. So shielding says our core electrons are going to block our nucleus from attracting our valence electrons. So back to my picture I drew over here. Okay, so here in the center, remember this nucleus is going to be attracting those outer electrons. So if my valence electrons are out here, that nucleus is attracting those electrons. And that is a really important role that they're able to play. But because there are these inside electrons, they're also being attracted to the nucleus. They're also repelling the outside ones. So they're interfering with the nucleus' ability to attract those outside electrons. And this one happens to have 2 inner shields. And so every energy level increases your shielding. And every energy level is going to interfere a little bit more. So even though that my nucleus is increasing here, so I actually have more positive charges as I get more electrons on the outside, it's going to be blocking it even more. And now look, just like naturally, as I move those electrons, you see it has to get bigger. These are both further from the nucleus, and they have more shielding than before. So that decreases your effective nuclear charge. And as your effective nuclear charge is decreased, that impacts so many other things. Think about polarizability, which we've talked about a billion times now. The fact that these outermost electrons are just so far, that nucleus can't have the attraction on it that it would have on these innermost electrons. Thank you, ma'am. Is that what you're going for, that one? Questions on that one? Okay, what other questions do we have? Over here.
solution formation.
Mira, what's yours?
I was wondering if you had a practice moving around.
Okay. I was curious if they had anything in relationship to each other. All right, so you two voted on having the individual sessions and everybody else is simply, I think that's kind of funny. That's making me laugh. All right, so I don't want to forget limiting reactants. We'll make sure we do that. So I'm just going to write it here. But we'll do solution formation first. As far as like,
I don't really know what, I wrote it down for that part two, and I didn't really know exactly.
If I were going to talk about solution formation, I'd say it would be probably somewhat similar to the FRQ you guys just did about the idea that your electrons, that's what I'm going to say, your charges are going to be oppositely attracted together. So the FRQ we just did with the water being able to surround it. Okay, and so we're all on board with water has 2 hydrogens and 1 oxygen. We're going to work with that. Okay. Then let's do limiting reactants. Sound good? Okay, limiting reactants. Any chance you have a problem off the top of your head, or do you want me to just make one up?
I think
I can also just make one up. Let's say we'll do an anionic equation too, if you guys are okay with that.
Oh, yeah.
Solutions. Calcium hydroxide. Oh golly. I should give it some amounts. Let's say 100 milliliters, 2.5 molarity calcium hydroxide. Oh my gosh, that hurts my shoulder. So I made this problem up. A solution of, I was going to do 2 solutions and then I switched it. Solution of 100 milliliters, 2.5 calcium hydroxide reacts with 15 grams of zinc metal. So the first thing you have to do is write your equation. We're going to do it as a balance or a net ionic equation, mostly just because we want to practice that. You would probably be fine to solve this problem not as a net ionic equation. So when I go to write my reactants, I'm going to base it on the information from the problem. Calcium's a +2 charge. Hydroxide is a polyatomic ion, so you have to know that. This is one that I would have assumed is a pretty common one for people to know. Hydroxide, carbonate, nitrate, phosphate, sulfate, anything that ends in 8, you should for sure know those. And then calcium hydroxide has to have the 2 down there so that your charges cancel. And up here, I was told that it's a solution of sodium hydroxide. So listen to what it says and believe it. Even though calcium hydroxide, if I hadn't told you so, you would have expected it to be a solid. Like if you were just going to predict its state of matter, I would expect you to say solid, but I told you a solution, so go with it. And then zinc metal would be a solid. So in a net ionic equation, my goal is, well, any equation, I need to mix these up so that I have new reactants with new products. So if I put zinc and hydroxide are now going to go together. And I know that they're going to go together because calcium and zinc are both metals. So the ones that are alike need to switch places. And so zinc and hydroxide are going to go together. And then that'll leave me with calcium next in the mix. This isn't a very good net ionic equation. We'll do that. All right, so zinc is going to be, oops, jokes. So zinc will be hydroxide also. It has to have a 2 next to it also because zinc is a +2 charge. And make sure you get rid of that. But you need to know that zinc has a +2. It's not one of those transition metals that you should just be familiar or that you have to be told the charge of. Zinc is one you should know. And then calcium, because it's becoming a metal, it's not going to have a charge to it. So you wouldn't put a charge here. This would be just solid calcium, just as zinc here didn't have a charge. But now zinc does. And so when they go to change their charge, you, if zinc became charged, calcium has to become uncharged. Remember, that's like transferring your electrons. So if somebody's losing electrons, somebody else has to gain electrons. So you want to make sure you keep track of that. What state of matter should zinc hydroxide have? It would be a solid. Why would you guys guess it's a solid? Yeah, it doesn't have sodium or any of my alkali metals. It doesn't have my nitrates. It doesn't have aluminum. Remember, those are the ones that are always aqueous. And if one of those are present, it has to be aqueous. If none of these are present, then you would call it a solid unless you were told otherwise. So then in a net ionic equation, we would typically balance both sides. This happens to be balanced already. And then anything that's aqueous and only things that are aqueous, nothing else, only things that are aqueous, would you separate into their two charges? Because you're showing that, just like we were talking about with solution formation, that those ions actually dissolved in water. Those ions were actually separated, that they're not hanging out together, stuck to each other. They are actually floating around separately in the solution. Zinc hydroxide I would not separate because it is not dissolved in water. So it is not separating around with the ions, with the water. So this would be my net ionic equation. Yes, sir.
Do you have to write the dates and math in a second?
I would. I like it when you write it in there, but it's not going to be really useful. Okay. So here's my equation. Now, if I wanted to do limiting reactants, I would take my information that I was given. There's a lot of ways we could do the limiting reactant problem. If you were just trying to solve for your limiting reactants, there's like option A. You can take the information you have of one and figure out how much you need of the other using stoichiometry. And then if you have that much, great, the first one was limiting reactant. If not, then the second one was. Or you can set up two different charts and solve for one of your final products and see which one's smaller. Do you guys have a preference? Which way I show it? Anybody care? What? That was going to be the one I picked. All right, so if we're going to start, I'm going to start with 100 milliliters of calcium hydroxide. Why did I start with 100 milliliters of calcium hydroxide and not 2.5 molarity? Okay, good. So I could actually have started with both. And in fact, I'm going to start the second T-chart with my other one, 15 grams of zinc. But I want to start with milliliters instead of molarity because molarity is going to be a conversion and it's a way to switch from moles to liters. So very rarely would you start with molarity as your beginning number. Mostly the only time you would do that is if you just don't have any idea where to start, then you might as well start somewhere. But typically you wouldn't start with molarity. Okay, so we've got 100 milliliters. We know since molarity is our moles per liter, remember 2.5 molarity means I have 2.5 moles for every 1 liter. So this is going to become a conversion that I use in my chart somewhere. If this is milliliters, I need to either switch it to liters before I put it in, or I need to do some sort of way of converting my milliliters to liters. If this is 2.5 moles in 1 liter, it has to also be 2.5 moles in 1,000 milliliters. Is that true? Okay, because I'd already written that, I'm just going to do this. So this tells me if I had a beaker of 1,000 milliliter beaker, I had 2.5 moles of calcium hydroxide mixed inside that. It's all dissolved around. And then I'm going to use a mole ratio to go from moles of calcium hydroxide to something. This particular problem, I didn't actually ask a question, so we weren't solving for any particular value. In this instance, we're making 2 different solids, which is weird, but let's figure out let's figure out the number of grams of calcium metal solid. Okay, let's figure out our number of grams of calcium solid. So if I go from 1 mole of calcium hydroxide here in my equation, I need to figure out how much calcium I would make. Unfortunately, because of the equation I picked, these happen to be a 1-to-1 ratio. But remember that when I do my mole ratio, I'm picking out these numbers that are here in front as my coefficients, because that tells me how many of these it takes to make how many of those. That'll give me my moles of calcium, and since I'm looking for grams of calcium, then I would go to the periodic table and figure out how many grams. So we'll solve that out. We'll do that in a second. I'm going to do the exact same thing down here and say, well, this information told me how much calcium I can make with this much calcium hydroxide. I have to figure out how much calcium I can make with this much zinc. And then whichever one makes the smaller amount is my limiting reactant. Can you not see? I need to go higher. I don't have anywhere else to go higher. All right, sorry. I'll try to do a better job. So 65 grams of zinc. I need to switch to moles of zinc. The whole goal of switching to moles of zinc is because moles have to be the unit that we're in and able to actually convert and compare things. So anytime you're in grams, I would guess that you'll probably have to switch it to moles at some point. So just be prepared for that. And yeah, that's where you use your number from the periodic table. Then now, because I'm trying to get to calcium to figure out how much it is, this is where I'm going to use my balanced equation and pick out my mole ratio. Once again, it's going to be 1 mole of zinc. Make sure we're using just the one from your reactant side, not the zinc hydroxide side. And then from 1 mole of calcium, and then I'll go back to grams again. Isabel, are you calculating?
Yeah.
Thanks. Go for it.
So if it's asking you for grams of calcium solid, how do you answer the question? Do you say that like either one of them would be reactant, or like how do you answer that?
Well, like if I said how many grams or calcium would be formed,
Yeah.
then you would just say you could X through one and put a box around the other one and say it will form 40 grams of calcium metal. What'd you guys figure?
For the top one, I got 10 grams, and then for the bottom one, it was 9.23.
Okay, so let's think about significant figures here for a second. Let's pretend like I put a decimal after this guy there and a decimal there. So when I go to multiply my numbers out, how many significant figures should my answer have in the 10 grams one? 3 significant figures. So is this 10.0?
Yeah.
Okay, so we got 10.0 grams of calcium. Could be formed if I reacted all of my solution of calcium hydroxide. If I reacted 15 grams of zinc, it could make 9.23 grams of calcium. So between those two, how much calcium am I actually going to be able to make? 9.23. Because I will run out of zinc once I get to 9.23 grams, and so the reaction will stop. So when I'm told it makes 9.23 grams of calcium, that's kind of what I do. You could almost just even leave it like that if you're running low on time. It's a weird question that you would just be asked this. Like probably it would be a situational based, like maybe you would say, now that I've found the answer, you could say like you measured out 10 grams of calcium in the lab and you'd be asked to calculate your percent yield, or you would be able to compare the amount of solid versus what you expected to do. Something like that you might have to do. So probably you'd have to do some more than just like a straight up limiting reactant problem. Questions on that? What? Do you have another question? Okay, well, we have 3 minutes. Yes.
Just so this is like an example.
Do you have one? Find me one, Amira.
This is like maybe able to story down.
This one is?
Yeah.
Yeah.
Like unit 2 for that question.
I don't have my FRQs memorized. I'm not like, I'm just like answering the questions you guys ask. I told you it had to do with molarity, so you'll for sure have to do something like this.
Okay.
Yeah, I think so.
Oh, could you do a reaction really quick?
Yeah, I think Amira is looking for one for me. Oh, unless you have one.
I just passed the worksheet. I can find one actually.
Somebody has one they could throw out. That's harder for me to just make one up. Like do we have one that's maybe a whole equation written out?
You do after school.
Here, do you want the worksheet?
Yes. Oh. I think these are harder than the ones you would have on the test. I don't know if I can do this one. Let's do this one. Okay, so in this particular one, when you are going to balance this equation, we're doing a redox. And so our goal is to figure out first who's gaining electrons and who's losing electrons. And so when you do that, if you have oxygens in it, chances are that's not typically the one that changes. And remember, when you have an element that's all by itself, its oxidation state is 0. So we know aluminum and manganese are the ones that are going to be doing their changing here. So you can even just jump right to those and ignore everything else. And so here, manganese is bonded to 2 oxygens, which we know have to have an oxidation state of -2. Times 2 gives me -4. So manganese's oxidation state has to be a +4 to cancel that out. Oh, this one's gonna be a +6. You guys just want me to, I could tell 6th hour we need to start with this, or we just finish it. Okay. Yes, same thing. Sorry. +3 for aluminum specifically, but it'd be +6 for its side. And then because I have 1 aluminum here, but 2 aluminums here, I have to start with balancing that out to take care of that. So, do you guys just want to pick this up later? All right.